All right, in this video, we're going to try to review the concepts that are in Unit 7 of AP Calculus, which is differential equations. So there's going to be a lot of links as we go along. I'm probably not going to solve that many problems. I'm more going to describe ideas, what you'll see on the exam, that kind of thing. But look for the links, and that'll take you to a bunch of problems, examples, me solving them, and things like that. So let's get started. So I'm going to follow basically the course description as I go through this. I'm going to do just the AB stuff in this video, and then I'll make another video down the road for the BC stuff. So here we go. Differential equation is literally just an equation that has a derivative in it. So the derivative being in it just means like y prime or dy dx or a second derivative or any order derivative. So you'll see things that look like any of these. Y prime equals x. Dy dx equals x squared times y. That's a separable differential equation. Dy dx equals x cubed plus 3y squared. You will not know how to solve that when you're taking AP Calculus, but you'll still be able to analyze things based on it. And then you can have even weirder things like y double prime minus 3y prime plus 2 equals 0. For things like that, you mostly verify solutions. But it's really important to know differential equation, just any equation that has a derivative in it, which means every time you take the derivative of something, you're essentially creating a differential equation. So let's look at the first thing that you have to do with differential equations. According to the course description, you kind of do a lot of stuff with differential equations before you get to Unit 7, in my opinion, like approximating values of a function with a tangent line, things like that. But here we go. 7.1 is modeling situations with differential equations. So what does that really mean? That mostly means translating words into equations. And then sometimes you have to solve them, but sometimes in the multiple choice, for example, you really just have to read a situation and choose the differential equation that it represents. So the first one that I think is really important to know, that isn't stressed all that much, but that a lot of people find confusing, is the differential equation that represents linear growth. So you'll have a population and you'll be told the population is growing linearly, or which of the following differential equations represents linear growth in a population, right? So when that is given to you, when you see those words, linear growth, it actually just means that the rate of change of the population is a constant, right? Because what has a derivative that's a constant? It's a linear function. So the population, if you were to plot it over time, would be a line. Its derivative is a constant. So the differential equation that represents linear growth is dp dt or dy dx, d whatever equals k, a constant. All right, the next one is the one that's really emphasized in AP Calculus, certainly in AB, but it's just as important in BC, is which differential equation, or what is the differential equation for exponential growth expressed in words, right? So you're going to have to be able to read this and then turn it into a differential equation. So these are the words for that. The rate of change of a quantity is proportional to the size of the quantity. So the rate of change of a population is directly proportional to the size of the population. The quantity of grapes is, directly proportional to the number of grapes that you have. That doesn't make any sense, but those words would translate into an exponential differential equation, the differential equation for exponential growth. All right, so what does the equation look like? Well, the equation is pretty famous. So it's going to look like dy dx is equal to k, some constant, times y. That's the differential equation. So you have to know that. When you read the rate of change of blah is proportional to the size of blah, or the rate of change of blah is proportional to blah. That's the same thing. So it's usually like dy dx equals k times y, dp dt, the population over time, is equal to k times p. It's just that the dependent variable, huge screw up there. The dependent variable is the variable in the differential equation, right? So it's dp, p is the dependent variable, and then it's a function of p. So here we have dy dx equals k times y. Hugely important. And then you could just be thrown like any random little thing. So for example, you might see something like the rate of change of the volume over time is proportional to the reciprocal of the cube of the volume. And you're just like, what? Well, it's saying the rate of change of the volume over time, so that would be dv dt, and then is directly proportional, that's k times something, and it's the reciprocal of the cube of the volume, so 1 over v cubed. In my experience, there will never be a problem that says inversely proportional. It'll always just say proportional, and then if it's supposed to be inverse, they'll just say it's directly proportional to 1 over the thing, which is good because it's just like fewer words that you really need to memorize and think about. All right, let's move on to the next thing. So going to go through the entire thing. I expect that you'll probably not watch the full video straight through. Maybe you watch a little bit here and there, or put it on in the background and just let it run. I'm going to have timestamps, so you should be able to jump around and look for a lot of links down below eventually. All right, 7.2 is verifying solutions for differential equations. And I am like not a huge fan of this because unless it's really straightforward, it's a ton of work, but that's okay. We need to know what the solution to a differential equation is though. So according to AP Calculus, the solution to a differential equation is 1, a function. So it has to be a function that is continuous on an open interval containing the initial condition. So part 2 there is kind of a lot. So it needs to be continuous on an open interval containing the initial condition, the x of, so you're given a differential equation, you're given a point that it goes through. The x of that point needs to be in the domain of the function, obviously. The y value from that point also needs to be in the range of the function that you're checking. And so you need to know the definition so you can kind of work with it. And I'm thinking more for multiple choice here, but they definitely come up in the free response. So here are my strategies. First one, check the domain. So what do I mean by that? Here's an example problem with like 2 options. dy dx is 1 over x and y of -1 is equal to 0. So -1 is the x value, 0 is the y value. 2 possible solutions for this would be y equals the natural log of the absolute value of x where x is greater than 0, and, or I should say, y equals the natural log of the absolute value of x where x is less than 0. Well, we need the domain to work, right? So we need -1 to be in the domain of our solution, so we're going to have to choose this because that's the solution that allows x to be negative. So just checking the domain on multiple choice, sometimes you can eliminate half of the options, so you should always be on the lookout for that. You should also just check that the initial condition goes through the options on multiple choice, which frequently there's one where it just doesn't. All right, the second thing that I would usually do on these is I would check the range. So I'm doing this where like I'm just verifying the solution. I'm not actually solving it. Like I have a multiple choice problem where I'm given dy dx, dy dx is x over y and y of 0 equals -1. Which of the following could be the solution or is the solution? So in this case, I'm given 2 choices. Y is equal to the square root of x squared plus 1 or y is equal to the negative square root of x squared plus 1. So in this case, they have the same domain. The question is, like, which of them allows you to actually go through the initial condition? Well, since when you plug in 0, you need to get -1, only one of these options allows that to ever happen. So we have to pick that one. So we're going to say this because it's the only one that lets you go through -1. When x is 0, y will be -1. So you got to check the domain. You've got to check the range. Don't be afraid of verifying solutions. It's kind of weird, but like it's pretty straightforward. So the third thing that I'll do, and this one is, well, I mean, I guess I would do it on the previous 2 too. Just start taking derivatives and plugging into whatever you were told, right? So an example problem where I would definitely do something like that is to verify that y equals 8e to the -9x is a solution to the differential equation y double prime plus 9y prime equals 0. Like, we don't know how to solve that differential equation, but what we can definitely do is we can find y prime, right, from y equals 8e to the -9x, just chain rule problem. Find y prime, we can find y double prime. We can take both of those, plug them into the differential equation, and see that it gives us 0. If it gives us 0, it's a solution. If it doesn't give us 0, if we end up with like, I don't know, 72 is equal to 0. If we don't get 0 equals 0, then it's not actually a solution. So we can verify just by substitution, right? That's kind of like an Algebra 1 student might think to do that. They wouldn't know how, but they might think to do that. And then the fourth thing to keep in mind here for this particular topic, I think, you don't need to be able to solve the differential equation to verify a solution. you will be given the solution and told to verify it. Now, you might be given 4 possible solutions, like number 3, that differential equation there. I've seen multiple choice where they say, like, which of these options is the solution to this differential equation? I don't know that there's a fast way to do it other than starting with A, find the first derivative, find the second derivative, plug in. If that doesn't work, move to B, find the first derivative, second derivative, plug in. But you don't need to be able to solve it to verify a solution. That's something really important to keep in mind because my students frequently try to solve things when they're not meant to solve them. They're just meant to verify them. So that's something you would want to keep in mind. All right, let's take a look at 7.3. So 7.3 is something that I kind of enjoy, but also kind of hate. So it's sketching slope fields. Computers, calculators, they're basically designed to create slope fields. Humans are not really. But when I think about slope fields and I think about sketching a slope field, I know what they're going to end up looking like. But what I really think is this is a ton of point slope tangent line problems, right? I am given multiple points. I'm given the ability to find the slope at those points. And then what I'm going to do is draw a little tangent segment right at that point. So my advice for you here would be just aim the best you can. It's going to be kind of tough because often the slope takes you like off the grid. I'm going to do one in a second, but so aim the best you can. Make sure if the slope is supposed to be 0, that you definitely get that right. Everyone grading a slope field that you have generated will always be looking to see, is the slope 0 where it should be 0? After that, honestly, people pretty much look, is the slope positive where it should be and negative where it should be? And then, depending on how picky you're being, you might kind of like take off a point if they're obviously not steep enough, but that's getting picky. So let's do one. So here's our slope field. It's got 9 points. That's like the maximum they would ask you to do. dy dx is equal to x plus y. All right, I'm just going to fill this in using a couple of techniques. I'm going to look at, first of all, I guess, if y equals negative x. So I'm just picking, I'm like looking at this, and I'm saying the line y equals negative x goes through 3 of the points that are on this grid. So let's see what the slope is like along that line, right? If y equals negative x, then you get x plus negative x by subbing in. So you just get dy dx is 0. So I can actually fill in 3 little horizontal lines there, right? That's what I mean by tangent lines. Those are the tangent lines, right? At the point negative 1, 1, I would get a horizontal line. At the point 0, 0, I would get a horizontal line. At the point 1, negative 1, I'd get a horizontal line. So I just draw a little horizontal line. All right, now I'm going to look, I guess, along the axes. So like if x equals 0. So if x is 0, then dy dx is equal to just whatever the y coordinate is, right? So when x is 0, you get whatever the y coordinate is. So when you're at like 0, 1, you're going to get a slope of 1. So how do you do a slope of 1? Here's what I do. I just kind of like aim. So I'm aiming for that point. Like I know that if I go through those 2 points, I would get a slope of 1. So I aim for that point, but I only draw the little tangent segment. And then at 0, negative 1, it's kind of the same idea. You get a slope of negative 1. And I'm just going to aim down there and then actually draw the segment where it should go. So that's what I'm doing when I draw these things. We have what? We have 2 more points, no, 3, 4 more points. If y is equal to 0, what do? If y is 0, what does dy dx become? It just becomes x. So when you're on the x-axis, where y is equal to 0, you just get a slope of whatever x is equal to. So if you're at, I forget which one I did first here, probably negative 1, 0, probably not, we'll see. There you go. So at negative 1, 0, we already had like that place to aim, so I just filled it in. At 1, 0, we get a slope of 1, so I'm aiming, I'm skipping stuff here. That was actually, hold on, let me go back. Okay, so the last point is 1, 1, and at 1, 1, you get a slope of 2. 2 looks very steep on this slope field, right? So what I'm going to do is I'm going to aim between those points and then just kind of erase in my mind. So like, that's what I'm really doing. I draw the line and then I erase it. Here, I'll go back and do it again. Draw the line, draw the segment, erase the line. That's basically what I'm doing. And there you have your slope field. Is it a useful slope field? Not super useful, but they ask you to do it, whatever, you do your thing. All right, let's talk about 7.4. So 7.4 is, there's one more, sorry. And the last one is at negative 1, negative 1, where the slope is negative 2. Classic example, There's nothing to even aim for, so just do your best and draw like a line segment. There you go. It's kind of steep and it has a negative slope. That's all anyone really looks for. All right, so errors aside, let's now look at 7.4. So 7.4 is reasoning using slope fields. So this, in my mind, is mostly like matching a slope field to a differential equation, sketching a particular solution, describing the particular solutions, like are they concave up, are they concave down, are they horizontal, are they generally increasing, generally decreasing, do they have a relative minimum, a relative maximum, like all of these sorts of questions. But if you can sketch particular solutions, I think you'll be fine. So to start with, I'm just going to suggest that you watch my matching slope fields to differential equations video. It's actually 2 videos. I go through like a ton of problems. I explain all of my reasoning as I match them. I think it's well worth your time because those are just free points on the AP exam. So check that out. The other thing is we're gonna have to sketch particular solutions. So when I sketch a particular solution, what I picture in my mind is that the slope field is this flowing water, and I'm just gonna drop a leaf in the flowing water and see where it goes. So that's what I do. So here's a slope field, and what I'm gonna do is I'm gonna draw the particular solutions through A, B, and C. So I'm thinking of this as just flowing water. I'm gonna drop a leaf into the water at the point A, and it's just gonna kind of go that way. But it could go to the left. So you do have to go like, as x goes to negative infinity, as x goes to positive infinity, what happens? You get a linear solution there. Linear solutions are pretty interesting because they tend to be the dividing line between your 2 types of solutions, or 3 types of solutions in this case. They also tend to be the asymptotes of all the other types of solutions, as we'll see when we do the other ones. So let's picture flowing water. You're going to drop a leaf in at the point B. And if you go to the right, you're just going to kind of approach there. If you go to the left, it looks to me like you're just going to plunge to negative infinity pretty fast. And that's just, that's what water would do that. Think of another point that's down there. Put a point in there and see what would happen. Same deal. What if we do C? So if I go to the right, it looks like I'm going to decrease for a while, hit a minimum, and then go along that linear solution. So I think it's going to do this. And if I go to the left, it looks like I'm just going to go up like real fast. Kind of like this. Those, I think, are the 3 types of solutions. So you want to be able to sketch solutions, look for where there should be minimums, look for where there should be asymptotes, try to get concavities right. Those are the things that you're trying to do. Nobody's really perfect on those, so don't stress about it too much, but make sure you can do it. And then these are the things that I, go watch the video, but these are the things that I look for when I'm trying to, match a slope field to a differential equation. Remember, the differential equation, you're looking at all the solutions to the differential equation. So if you think the solutions look like x squared, the differential equation is 2x. It's the derivative of what you think the solution looks like. But I look for zero slopes or horizontal lines, linear solutions, slopes in different quadrants, is the slope always negative in a particular quadrant? Is it always positive in a particular quadrant? And then I'll just test points, but can't stress it enough. Just go watch these videos. It's definitely worth it, especially if you're studying for the exam. Let's take a look at the next thing. So the next thing for us is going to be 7.6 because 7.5 is a BC only topic. I think it's Euler's method, and I will cover that in a different video. Actually, I have another video about that already, so I'll just link it below. But we're going to skip that because we're doing the AB stuff because it covers the most people, and then we'll come back to the other stuff. So 7.6 is finding general solutions using separation of variables. So to solve differential equations in Calc AB, you pretty much only know 2 ways, I'm going to say. Well, 3. Well, okay, there's a lot of ways, but one way is you look at the differential equation and you just know the answer, right? If you look at a differential equation, it's like dy dx is equal to cosine of x. You're like, oh, y is equal to sine. You solved it, plus c. Don't forget your plus c's. Don't be that person. The other way is you reverse the power rule. You do that all the time. And then the third way is basically separation of variables. Those are kind of your options. A differential equation is separable if it looks like this. dy dx is equal to f of x times g of y. You need to be able to write it as a product of a function of x and a function of y. So for example, you could have something like, these are all separable differential equations. dy dx is equal to 3x squared times y. dp dt is equal to k times p, that's exponential. dv dt is equal to 1 over v squared, it's separable. You can also have like things that look like the quantity x plus 2 times the quantity y minus 5, things like that. Those would also be separable. Things that are not separable, that you will still run into, you're just not expected to solve them, are basically things that have addition and subtraction between variables. So dy dx equals x squared plus y, not separable. dp dt is equal to p minus 2t. It's not separable. It doesn't mean you can't like find the second derivative and use the second derivative test to determine if there's a maximum or a minimum. You could write a tangent line given a point, right? Because you can find the slope. You just can't solve the differential equation. Not the end of the world, but you can't do it. All right, if you're going to solve these things. Basically, I have a lot of videos about this. I recommend you check those out as well, but I'm going to this is my general method, is to separate the variables. So if it's dy dx, everything with a y goes on the side with dy, everything with an x goes on the side with dx. If it's dp dt, everything with a p goes on the left side or with dp, everything with a t goes on the right side. dv dt, the dt goes across, the v squared comes up. I'm looking at the example above. So separate, and then you just do two antiderivatives, and you kind of hope that you know how to do that, right? So you might get arcsine, arctan, natural logs are extremely common. Do not forget to put a plus c. You only put one plus c, and you put it on the side with the independent variable. So the independent variable is the variable that's in the, I'm going to just say the denominator of dy dx. So dy dx, x is the independent. dp dt, t is the independent. I don't know if it's the rate of change of volume with respect to area, like dv, dA. A is the independent. It's the with respect to, that's the independent. That's where plus c goes. And then you have to make sure that you have an actual function. So you can't get y squared is equal to x squared plus 1. That's not a function, so it's not actually the solution. It's really that y is equal to plus or minus the square root, and then you determine the plus or the minus based on the range, which we talked about for verifying solutions. So that's the method that I follow. I have a lot of videos on solving differential equations. You should definitely check those out. Also, there's a lot of free response questions that are differential equation based. And I think I have a playlist of those, and I'll try to link that below too. So also, you want to do all of those before the exam. You want to do all the free response questions. I know that sounds like an impossible task, but it's really what you want to do. All right, let's take a look at 7.7. 7.7 is finding particular solutions using initial conditions. It broke my heart one year. One of my best students ever, days before the exam, is just I don't know what it means when it says find the particular solution. I was like, oh no, find a particular solution really just means solve the thing and solve for C. That's all we really need. The initial condition is the point that the thing goes through. The other thing I would say about finding the particular solution is you do also need to worry about the domain and the range. Domain in particular is the trickiest thing that comes up that people tend to just forget. And you have to remember the solution to a differential equation, what it means. This is review just from this video because we covered this before, but the solution to a differential equation is a function. So you can't have y squared, you can't have 1 over y. It's a function that is continuous on an open interval that contains the initial condition. So vertical asymptotes screw up continuity. That's really the main thing to watch out for. You got to be on the side of the vertical asymptote that contains the x coordinate of the initial condition. I have a couple of general tips about these, and then these, if you watch the other videos for actual problems, tons of those. The first tip, if you have to exponentiate to solve for C, to solve for y, it should say there, that's a mistake. If you have to exponentiate to solve for y, let me change it. It's really annoying to change this on the fly, but I'll do it. Here we go. If you have to exponentiate to solve for y, then exponentiate first, then solve for C. Exponentiate before solving for C. That's my advice. So it might look like this. the natural log, the absolute value of y is equal to x squared plus c. You solve a differential equation, you get to this point. Wait, do not solve for c yet. Now, for reasons that I explain in a lot of places, this becomes y equals ce to the x squared. Now you would solve. That's where I would solve. If you have to exponentiate, do it before you solve for c. It makes your life a lot easier, especially regarding the range of your solution. So exponentiate first, then solve for c. All right, 2 more tips related to this. First of all, multiply by 1 if it is not obvious what you need to do. So people get a little stuck on things that look like dp dt equals p plus 8. Like they want to subtract p from both sides. That's not what you should do. What you should actually do, like there's no t anywhere, right? So what I'm going to do is I'm going to introduce something that could be times t. So I'm going to rewrite this thing as dp dt equals 1 times the quantity p plus 8. Now it's a little more obvious what I'm leaving on the right-hand side when I separate. So it becomes dp over p plus 8 equals 1 dt. And then you integrate both sides. So multiply by 1 can actually make life so much easier. And it avoids a lot of mistakes. So I will do that all the time. The other tip I have, factor out a negative because it leads to fewer mistakes. So what I mean by that is specifically this type of differential equation, dw dt equals 6 minus w. So this is actually kind of like the last tip as well. There's nothing really obvious to be times t. So what I'm going to do is I'm going to rewrite the differential equation, just factor out a negative. dw dt is negative quantity w minus 6. Now, 2 things happen. It's kind of obvious that I get negative 1 dt on the right-hand side. And on the left-hand side, I get dw over w minus 6 instead of 6 minus w. There's a u substitution that people forget to do when it's 6 minus w, right? 6 minus w is equal to u. So negative dw is equal to du. There's an extra negative sign floating around. I took care of that by factoring out the negative to begin with, and now I don't have to worry about that u substitution. So by doing this, you are avoiding that mistake, which I have seen so many of my students make. You don't want to make that mistake. So another thing to think about, I don't actually know where it is in the course description, but it's got to be there. Some functions have no simple antiderivative. You can still, quote unquote, solve the differential equation, but not like explicitly. You don't just get like y equals x cubed. So what you do is you just use the fundamental theorem to make an accumulation function. Accumulation functions are totally acceptable solutions to differential equations. So for example, if you see dy dx is e to the negative x squared and y of 0 equals 3, you look at e to the negative x squared and you're just like, I don't know how to integrate that. In fact, no one really knows how to integrate that. It doesn't actually have a simple antiderivative, but we can still write a solution. We can still say y is equal to something. What we'll say is y is equal to 3, which is what you start with, plus the integral from 0 to x of e to the negative t squared dt. And now, just grab a calculator and it can tell you values of this function. You can find the derivative, the second derivative. It's totally valid. It just doesn't look like the functions that you met in like pre-calc and down, right? You never saw a function like that, but they're functions. You can also see it even weirder, where it's like much clearer that you cannot find an antiderivative. dy dx is equal to f of x and y of 5 is equal to 2. Like, what are you going to do? There's nothing you can do except just write something like this. 2 plus the integral from 5 to x of f of t dt. Right? Just don't be afraid to use accumulation functions. It's especially, so I do this in 2 places. One, in multiple choice questions, when you're looking at the options and you see an integral, you should immediately think like, oh, maybe you can't actually integrate this thing. Like maybe the other options are the common mistakes that people make, and the right answer is the accumulation function. The second place that I use this is in free response questions, which, again, do all of the free, like every one of them. Start in like 2000, I don't know, probably, I like to start in 2006 and go forward. It's a lot of problems, but, it's worth it. You run into this a lot in the free response questions, where you kind of basically have to write your own accumulation function and then reason about it. Like, where is it increasing, decreasing, concave up, concave down, maximums, minimums, absolute max, absolute min, all of those things. Anyway, let's take a look at the next thing. 7.8. So I think 7.8, yeah, 7.8 is consecutive. So 7.8 is exponential models with differential equations. That's how important the exponential model is, right? Remember, we had the linear growth. Linear growth is just dy dx is equal to k, a constant. Exponential, the words for it, which are super important, the rate of change of a quantity is proportional to the size of the quantity. And the equation was dy dx is equal to k times y. So y is our quantity. The rate of change of the quantity, dy dx, is directly proportional k times the quantity, which is y. So dy dx equals k times y. This has a solution that you can memorize, and you should memorize, but I always go through the solution process because it's super good practice. So what I'm going to do is separate and integrate. So I have dy over y is k dx. Throw some integral signs in there. And then we know this. It's the natural log of the absolute value of y is equal to kx plus c, because x is the independent variable, so c goes on that side. Now, we need to exponentiate to get to y, so we're going to wait to solve for c until we've exponentiated. That's where I had that, I wrote it wrong and then had to go back and fix it, you might remember. So this is going to give me y equals a new c, e to the kx. Now you need some kind of initial condition. So the initial condition I'm going to give is y of 0 equals y sub 0. I mean, it's lame, but it's what it is. So that means e to the 0 is 1, so you get that just y0 is equal to c, which means our solution, which you're allowed to memorize, is y equals y0 e to the kx. And you need another point if you're going to solve for k, and occasionally they make you do that. They used to make you do that like way more often way back when. You don't do it as often anymore, but you need another thing to solve for k. All right, so those are all of them. 7.9 is BC topic. It's the logistic differential equation, which I also already have a video of, so I will link that in the description, I guess, or maybe up above. I don't really know what I'm doing here. And then these are some closing thoughts on Unit 7. So first one is that 7.5 and 7.9 are BC only. In the description, there should be links. So check those out if you're in Calc BC. If you are looking to learn this stuff, like I went too fast, I'm sure everyone's going to say I went too fast, or whatever. If you go and look at notes 23 and 24 on my website, those cover all of that material in a lot of depth, and there are videos of me solving everything in those. I think that's worth it if you're a little shaky on stuff. And then my other advice would be just do every multiple choice question, every free response question that you can. If you're in an AP class, ask your teacher to give you access on Classroom to all of the available problems on those topics. And if you study hard, I think you will be fine. So this is a really long one. I hope you have found it helpful, and good luck.